This program is brought to you by Stanford University.
So I plan to talk for perhaps 35 minutes and then move on to a more interactive session with you. My topic is smart grids and decarbonizing the power sector. And what I'd like to do is to spend a little while talking about smart grids or smart power networks. The concept has been around for probably more than 5 years now, and I think it's important for us to try to actually unpack it and try to understand what it is that it really means and what progress we have made to its implementation. I'll then actually change a little bit and talk what I see as the various national energy policy priorities that are emerging, and there is quite a consensus there, and how the subject of my talk really is how smart grids can contribute to those national energy policies. One of the points I'd like to emphasize throughout this talk is that if you have enough money and enough ambition, in principle, smart grids can do anything. The question is, what do you want them to do, and what do you want them to do cost effectively? Because the sums of money involved in any of this major energy infrastructure are eye-watering. So I'll talk about what I perceive to be the 2020 targets as I describe them, which are converging on about 35% of electrical energy from renewables, and that's a target we can see emerging in a number of places throughout the world. Then the extraordinarily ambitious target that is also emerging by 2050, which is for greenhouse gas reductions of more than 80% on 1990 levels. And a key enabler of that is actually decarbonizing the power sector, which is the subject of my talk. And finally, I'll end up with a summary of where I think we are in terms of smart networks and list some of what I perceive to be the pressing research questions for the universities. So we start with the power networks. And these were really starting to be put together in the 30s. Interestingly, with the last major investment in the 80s. Privatization, deregulation, call it what you will, has not been particularly kind to the development of large power networks. Partly it's associated with the difficulties of getting planning or permitting permission, but it seems to me the commercial structure of the power industry has not actually helped. So what have we got? We've got large central generating plants generating and then putting the power up onto a high voltage network up to 765 kV in the US, and then shipping that round, but generally regionally. One of the, I think, misconceptions is that there is a strong, uncongested, unconstrained transmission system. That is not actually true either in North America or in Europe. Generally, these grids were regional or are regional. They were developed in national jurisdictions or to serve particular large conurbations and the loads. And if you try to trade between those jurisdictions or between those load centers, then you hit congestion. The other kind of key feature which the smart grid concept is challenging is that there is essentially no involvement of the customer in this process. Electrical energy is a commodity. Generally, it's at a uniform price. You don't interact with it hardly at all. If you've got an old-fashioned meter, you get a bill sort of occasionally issued by the utility. And so there is very little customer interaction in the process. There is also very little role for microgeneration or distributed generation. That's slightly changing, but in the traditional power systems, that is limited. The final aspects that smart grids is challenging very strongly is the use of ICT, information and communication technology. And there is a intuitive feeling that there should be much more use of ICT, particularly at the lower voltage levels, down at the distribution levels. And that's okay. The question that then gets asked fairly quickly is how to justify that commercially, particularly in the current structure. And it is very difficult to do so. Putting in wide area communication systems on the lower voltage networks are likely to be extremely expensive, and demonstrating the benefits when we are only a little way along our sort of policy objectives is quite difficult. So, if we have a look at what's going on, and I apologize, this is a European example, on the right-hand side, we can see the flows of electrical energy across national boundaries in Europe, and they really are quite limited. We are starting to engage in cross-border trading, but those of you who kind of, if you like, have an interest in the business will remember that perhaps 3 or 4 years ago, the whole of the north of Italy got blacked out. That's because there were large flows coming down from Switzerland. There were some problems with trees, and essentially they were overloading their transmission capacity for that energy trading. Generally, the transmission capacity between national jurisdictions is quite limited, and a key feature of smart grids at the transmission level is actually to remove those bottlenecks and create a more effective market. What the slide on the left is just trying to show is the massive investment that is going to come whether we do smart grids or whether we don't. The estimates vary, of course, but we are talking about something like 1,000 billion euros a year just to replace the aging asset base that we have throughout the world in terms of both generation, transmission, and distribution. It is not a question of must we or should we renew our electrical power supply infrastructure. The only question is with what do we make with what do we renew it? How do we make the new arrangements? So we have, or we are facing a number of really serious issues. On the technical front, we have this remarkably serious aging asset problem that has been there certainly for the last 15 years. And one can have gone to conferences over the last 15 years and people wring their hands and say, we have a major aging asset problem in generation, in transmission and distribution. What are we going to do? And the conversation hasn't really moved on during that time. We also, of course, have this congestion issue if we are trying to trade, and that becomes increasingly important as we try and establish open markets. And there is a technology pull. So we have a lot of new technology coming, a lot of new capability, particularly in the ICT area, but again, in my view, not too much clear understanding of how to use that technology. And I probably don't need to put this up in this audience, but we have two major issues on the environmental and socio-political front. We have increasing concern over greenhouse gas emissions, and that's driving our national energy policy, and equally serious concerns over the high and volatile fossil fuel prices and security of energy supply. So we have the triangle, which many of you will be familiar with, where we have security of supply concerns, environmental concerns, and the received economic orthodoxy that the most cost-effective way to address both of those is through free markets. And through free markets, both in terms of operating the power system, but developing the power system. And there is the hope, and this is, I think, going to be a point of debate, that free markets will actually develop the power system suitably and in the way we wish them to do so in the future. My personal view is that in terms of planning or the development of the power system, the demonstration that market forces as currently organized are delivering that appropriately and will deliver that in this very rapid period of change that we are going to go through. I think the jury is still out on that. So we come to the concept of smart power networks. So they can a number of features, but the first one is this coexistence of both large and small generation for both lower carbon generation. And in order to make that work, I think there is no solution or there is no alternative to efficiently integrating demand response, demand-side participation, call it what you will. As we go through this talk, I think it will become increasingly obvious that it is almost impossible to envisage this low-carbon power system of the future that does not heavily involve the load. I just don't think, well, you can make it work, but you make it work with massive amounts of plant. Plants are sort of 6 times as much as the average load. So fantastic numbers. In order to engage with that, we need to consider how we can actually trade using time variable tariffs and approach the sort of optimal operation of the system by engaging the customer. If you like, the consequence of engaging the customer using smart meters and bidirectional communications is that you end up with massive flows of information. And there is a very serious management problem, both in terms of the flow of information, if you like, on the part of the system operator, and as I'll point out later in the talk, a serious question as to how much information and in what form the customer actually needs and wants and is likely to respond to. There have been some smart metering trials in the UK. I'm sure there have been smart metering trials in many places, focusing particularly on demand reduction. And as one would expect, significant evidence of the rebound effect and that the customers get fatigue, and how to actually present that information to stimulate the response you want, I think is an open question. The benefits that we are likely to get or hope for is, first of all, insecurity of energy supply. And in the last year, if you like, the 2 pillars of energy policy, mitigation of climate change and security of supply, oscillate in terms of their importance. I think actually probably security of supply probably is preeminent just at the moment. But we're talking there in terms of using both large and small generation, and particularly using very large numbers of small generators while maintaining the levels of security and reliability that we expect. Obviously, in terms of greenhouse gas emissions, we hope for low carbon generation, we hope for combined heat and power or cogeneration, and all sorts of interesting innovations there in terms of limiting our climate change. One of the great hopes, of course, is the use of electric vehicles in terms of their ability to charge at times of surplus generation. And that's a very interesting area. Just illustration, one of the difficulties, though, of energy storage, which is it's a form of. And finally, there is a confluence of industrial policy with energy policy, that this is seen given that we're going to be investing 1,000 billion a year, a major opportunity for industrial policy. So if we leave smart grids specifically and consider what it is we might use them for, those are my understanding of the current energy policy environment in which we're working. And this environment, as we all know, sort of changes every 6 months. But at the moment, we have these two objectives. The first one I'll call the 2020 target, which broadly is that the number of power systems, most of the countries in Europe and a number of the states in the USA are looking for 35% of electrical energy from renewables by about that time. Now, we can trade whether it's 2020 or 2025, whether it's 30 or 35%, but that broadly is an immediate objective. And then we have the second, even more challenging objective, which is to decarbonize the power sector to contribute to this 80% greenhouse gas reduction based on 1990 levels. The first, I think we have a reasonable understanding of how we might get there. It's very challenging. We certainly need involvement of the demand side, but it is perhaps achievable. The second, it seems to me, is really open to lots of debate, and a major part of the university role, it seems to me, is addressing that second objective. Turning to the first objective, and there will be all sorts of different ways of doing this in different jurisdictions. The one that we are looking at the moment in the UK essentially is wind-based. I think it is very clear that by 2020, which is only 11 years away, we must use established technology. We must use established technology which you can buy on commercial terms. In order to get this massive investment, it's no use having a prototype machine. You must have something you can buy with a 5-year warranty and a 95% availability guarantee. And that seriously limits your options. So here we are looking at a massive increase of both onshore and offshore wind, with a modest increase in tidal stream, which was the subject of last week's seminar, some small hydro, and some biomass. So we are, in order to do that, we're looking at something like 14,000 megawatts onshore, 14,000 megawatts offshore, and major transmission reinforcement. And transmission reinforcement throughout the developed world typically takes 10 years. That's for the permitting and the construction. The construction will take 2, the permitting will take 8, if you are lucky. So and that is not particularly a British problem, it is throughout most of, as I say, the developed world. So what I'd now like to do is to go through how we might do this and what the role of smart grids might be. In terms of generation, the consequences of going to a 35% renewable power system is a very significant increase in plant margin. Because the capacity factor of the renewable plant will be low, it'll be around 30 or 35%, there's a lot more of it. If that's the case, then the operating hours of the conventional plant, which is there for the days when you need it, drop right down. And that potentially either reduces the profitability of the conventional generator or puts the price during those periods very high. So there are major issues associated with operating the conventional plant in this time of large plant margin. There's going to be considerable extra use of peaking plant combustion turbines with less efficient thermally. And the role of smart networks in this is to increase the demand-side participation and try to, if you like, smooth out these operating conditions. Because if you don't do this, you just, I mean, it's certainly possible to do it without demand-side participation, but you end up with significantly increased costs. That is one of the scenarios developed by the UK Transmission Authority for 2020. And the point I'd like to emphasize there, that on a 61,000 megawatt, 61 gigawatt demand system, they estimate you need 99 gigawatts of plant. That's a plant margin of 62%. A normal plant margin would, on a thermal system would be around 20%. You are significantly investing in plant which will only run for a small number of hours. In terms of transmission, there's going to be major new transmission routes required for both, in this example, both onshore and offshore. There are interesting technical innovations. We can talk about high voltage DC, and particularly voltage source high voltage DC, which is now available up to about 1,000 megawatts capacity at plus or minus 300,000 volts. There are all sorts of interesting ideas associated with improving the transfer capacity of AC lines, and those have been around really now for about 20 years. But we've only got 11 years to achieve this. So the immediate problem on which people are working really quite hard is how to change the administrative arrangements and the rules to make better use of the assets we have got. And in particularly, there are changes being considered both in terms of the allocation of transmission rights and in terms of the security of supply standards. At the moment, essentially, if you need 1,000 megawatts, you build 3,000 megawatts of capacity, so that if two of those lines break, the third one continues to operate. And that makes a lot of sense if you're supplying hospitals or high-value loads. It makes a lot less sense if you are just taking your electrical energy from intermittent renewables. That shows an interesting innovation given this difficulty of permitting. This is only under discussion. We have a major north-south transmission bottleneck we want to take a lot of wind energy capacity down from Scotland. There's a public inquiry that's been running for about the last 18 months over a small overhead line in Scotland. It will, I say, to build a new on-land overhead line route will take about 10 years. There is serious consideration being given to actually going offshore, submarine, using HVDC, primarily to sidestep the permitting problem. What it also allows you to do, conveniently, is to pick up some additional capacity from various offshore wind farms on the way. Finally, we come to the distribution level. A lot of this generation is going to be connected down at the distribution level, and there we have to move from the very passive, dumb, if you like, distribution circuits where there is no monitoring, there is no control, it is just lumps of copper and iron, to a much more dynamic and monitored system. The role of active networks there is becoming, or smart grids, is emerging, and there are a number of interesting research projects. That's a particular one called Aura NMS, where they're looking at using various controllers located at substations. But these visions are still, visions or experiments or trials or whatever, are still competing, and there is no uniform agreement as to how to go forward. And there is certainly no uniform agreement as to how to justify the expense of this kind of investment. So that, if you like, in a nutshell, is the 35% problem, the 2020 problem. I think we can see broadly where we need to go, lots of detailed work required, lots of contributions of many aspects of smart grids. And then we have the ambitions that were, if you like, articulated in our particular case last December. We had the Climate Change Committee, where the government is writing emission reduction targets into primary legislation. So this, I think, starts to get quite serious. And so where we are is that the 2050 target went from 60% to 80% of greenhouse gas emissions. And the way this was discussed by the committee was that they wished to decarbonize the power sector starting now and through the 2020s. I regret to tell you they didn't actually tell us how they were wishing to see the power sector decarbonized, but they wanted it decarbonized in about 21 years' time. And that is the position we are in. Now, the hopes are that we can do that with a combination of nuclear, fossil with CCS, and renewables. And let's talk a little bit about the characteristics of nuclear and fossil with CCS, post-combustion carbon capture and storage. Both of those essentially are constant output plant. So you have a combination of constant output plant and plant which is subject to the variations of the incoming energy flux in renewables. That is really very challenging when you are trying to meet a well-defined load. And you, as I say, it seems to me there is no solution to actually engaging in the load. And so if we look at what that might mean for the power system, on the generation side, we've got that combination of renewables and constant output plant. We must control the plant's margins by demand-side participation, storage, and perhaps better forecasting. I would point out, of course, although we can hope for cost-effective energy storage, it doesn't exist at the moment. And it has been an ambition of engineers for at least the last 50 years. So there is a question over energy storage. We have to involve the customer much more actively with variable energy pricing. And we have a particular problem of aggregating these very large number of small generators. At the moment, the control of the electrical power system at the generation level is done really on quite a small number of large generators. And it's quite an easy control problem at that level. Now we're talking about millions, and that's a big issue. Transmission and distribution will sort of merge together, and the differences disappear. We need to understand better how to connect and manage these very large numbers of small generators. There will be, if we are to use large-scale renewables, ever-increasing requirement for very large-scale transmission links. And we are going to see, I think, without question, much greater use of ICT in the distribution system, although I have, as I've indicated, justifying that commercially remains a problem, although it will become probably easier to justify with this particularly difficult generation mix. So finally, to come to my last slide, a few of what I see are the main some of the pressing research questions. The first question, which is not at all clear to me, is how are smart meters to be used? Do we want to use them for demand reduction, for energy demand reduction? Do we want to use them for frequency control? Do we want to use them for reserve? Do we want to use them for peak shifting? What is their function? I think when we listen to the smart metering enthusiasts, and I'm absolutely positive about smart metering, they tell you they can do everything. The question is, what should they do? And I don't believe that's resolved yet. We have this particular issue of the millions of small generators and controllable loads, and how are we going to aggregate them? The traditional power system engineer's response to this would be a hierarchical control structure. And that will certainly work, but will require an awful lot of communications. One question there, whether complexity science helps us with that question. A third interesting question, which takes us beyond the particularly engineering area, is how to communicate to domestic customers to actually engage them actively in demand-side participation. What level of information do they want? What level of information are they going to respond to? And a final point, which I think is interesting, and I hope I'm not going to get shot down too badly by the economists amongst us, is a market solution, both in terms of operation and development of a very rapidly changing infrastructure system, actually going to deliver what we want in the time available. So, Chairman, I think I'll stop at that point with those questions and look for contributions. Yeah.
A comment and a question.
Yeah.
The new generation of nuclear reactors can be ramped up and down in power in a few hours. So this business of having to run flat out is true of the old ones, but not so true of the new ones. And I think that needs to be factored into your planning. The second thing is a question on the correlation of wind. The British Isles is not so big. And when I asked Mark a couple of years ago about California, he told me if it wasn't blowing in the Altamont Pass, I'd probably have to go 100 miles to find a place where it was blowing strongly. Has there ever been a study using actual meteorological data on the correlations of wind? I can't find it, and I've been looking, but if the Brits are planning such a big thing, you need to do it.
Okay, can I come back on both of those? On the first point, I think I would reply that the only commercially available nuclear reactors on the market that I'm aware of anywhere are essentially PWRs. And the likely reactor that will be bought in Europe is the French, German, European pressurized reactor. The French have a limited capability to ramp that plant. It is a massive device. It's got a generator of 1,800 megawatts on a single shaft. Broadly, that will run base load on our power system. So in terms of looking forward within 20 years, I think that's where we're going to be. And that form of generation is likely to run flat. Coming to your other point, there has certainly been a whole number of studies not using MET data, but actually outputs of existing wind farm data. And there is good data on, if you like, correlation between various wind farm outputs. That doesn't take away the requirement generally to have either some plant or control of the load to meet, for those conditions when there is no wind. And what that does for you is puts up the effective costs of that plant because its running hours are limited.
Yeah, what do you think about the role of ICT in extracting more capacity from existing sources of power like hydro?
Yeah.
For example, you got 30 dams along the Columbia River, you get better dispatch, you can extract actually better, more efficient capacity out of it.
What ICD allows you to do is to work your primary transmission assets harder. So you are passing more current, down a smaller number of conductors. The inevitable consequence of that is that your electrical losses go up. Your plant utilization goes up, so that's good. Your electrical losses go up, so that's bad. Generally, the power companies are extremely nervous, certainly at transmission level, of what's known as post-fault reconfiguration. What they want is a system that if they get a fault on it, they lose a line, they don't do anything, and the system stays operating. Now, you can work the system harder, particularly with things like phasor measurement units and better IC2, so that you get the fault, and you then reconfigure the system automatically after that. And that's certainly possible. Your risk goes up, and the electrical losses go up because you're working the plant harder. But certainly that is in, if you like, in one of the bullet points there, that the interesting ways to increase the use of your transmission assets. But as I say, the consequences are higher risk, which the transmission company will not like at all, and they will argue they're not paid to accept that risk. That will be the first fight, or an early fight. And secondly, there's this I squared R problem.
So, since we've got millions of generators, I'm wondering if you can talk about how they could self-organize without like a command and control. It's just a bunch of individual operations that talk to each other. How that works?
Well, at the moment, at the generation level, let us say, and I would believe this to be the case in California, the Californian system will be controlled on, let us say, 100 big generators. And clearly it is possible to actually communicate directly with 100 big generators. When we go to this new paradigm of having lots of these smaller generators that do not only provide energy, but provide services in terms of capacity and voltage and all sorts of things that we need, we have 3 million of them. And the research question, I think, is how do you organize 3 million generators to do what 100 are doing at the moment? And the engineering solution is you just have an enormous hierarchy. And we can all understand that conceptually, but it's not at all clear to me that that's the most cost-effective solution.
I was wondering your thoughts on grid-friendly appliances and the role of end-use appliances on the smart grid.
And this is a particular view, I think the portal is likely to be the smart meter. And then there is an unanswered question, is that does the smart meter then communicate directly to the house, through the house to the smart appliance? Or do you wish to go through the customer? And what level of customer control do you want? And that question is unresolved at the moment.
I was actually thinking of demand responsive loads, like there's a company, RL Tech in England, that's testing refrigerators. And
no, I'm familiar with RL Tech. And the UK system, we are slightly, we have the advantage in that the frequency of our system, because we're an island system, 60 gigawatts, is an indicator of the health of the system. If the frequency is dropping, we haven't got enough generation. If the frequency is rising, we've got too much generation. And so what responsive load in that sense does is it just measures the frequency and then acts directly on various appliances, particularly refrigerators. And in terms of giving us, let us say, 2,000 megawatts of what we would call frequency response, so if we lose a big generator and the frequency starts to drop, that's detected by all these fridges, and then we shed 2,000 megawatts of fridges, and the system recovers. There is a problem with this, and it's known as the payback problem, in that a domestic fridge is probably operating 20% of the time. So if you've got 1,000 megawatts of domestic fridges participating in your scheme, and you send out a signal, however, from the frequency or not, you'll shed 200 megawatts of load. If you leave those fridges off for half an hour and give them all permission to come back, you'll get a 1,000 megawatt block coming back. So that payback problem has to be addressed, and that probably requires bidirectional comms. You can't then just do it on frequency. So interesting idea, but once you're in the detail, it has some challenges. That's my response on that.
So, in response to question number 3, I was curious your thoughts of who owns the information on demand side. So, with the owner of this information, how they can communicate with or monitorize with the domestic consumer and the generator?
Yeah, exactly. It's a very good question. I mean, these are where we are in Europe, if you like. I mean, anecdotally. Enel, the Italian state utility, put in 30 million smart meters about 5 years ago. They did it as the last gasp of the nationalized utility, where the board could sit around in a smoke-filled room and say, that's what we're going to do. You can't do that anymore because everything is split up. They did it for all sorts of interesting reasons. They needed automatic meter reading because there's a European directive. They had a particular form of load control where you bought a 15 amp supply, and if you took 16 amp, it tripped, and then they had to send somebody on a bike to reset it, and they wanted an automatic way of doing that. And they had a major theft problem in some of their cities. So they justified smart metering on a very strange set of criteria, which doesn't actually translate into many places. The Swedes are putting in smart metering purely to comply with a European directive that you must give good bills every 30 days, and you can't have meter reader if you're going to do that. Yep. Sorry.
Yeah, in terms of the studies that have been done on smart metering, and what's been the estimated reduction in electricity used by customers, and what has been the rebound effect?
I need to refer you to a very good study by the UK Energy Research Centre which actually addresses that. I can certainly do that. It's a modest number of percentage, and the rebound effect is significant. That's my understanding. But the numbers are in a particular UK ERC study called the Rebound Effect.
You opened your talk with saying that if we had an infinite amount of money, we could theoretically do anything with smart grids,
yes.
And that the estimated amount of money that has to go in just to replace the existing grid is about 1,000 billion euros per year.
That's it.
Can you give a rough estimate of, if you think about adding on smart grid technology, what kind of range of additional costs are we talking about? Is it another 1,000 billion, given all of the different things smart meters could do? Is it much less? What kind of range are we talking about?
I can't answer that particular question because it's not a question, it's not a road we want to go down. If we take that 1,000 billion figure and add on that decarbonized power sector ambition, the numbers that we are discussing in the coffee bar at the moment is you'll multiply 1,000 billion by 6. So in order to meet that decarbonized power system, we think the investment will go up by a factor of 6, and that's purely sitting around in the coffee bar. The role of smart grids is to drop that down as far as possible towards the initial 1,000 million. And forgive me, I don't think anybody knows what that answer is.
On that note, let's draw the question to a close and thank Professor Jenkins.